Tutorial 4, Question 3. For the reaction shown below being conducted in a process with recycle, draw the process flow diagram and determine the composition of the fresh feed and the composition of the overall stream, leaving the process. In this process, after the products exit from the reactor, a stream of pure B is separated from the products and forms the recycle. The fresh feed is 20% in excess in A. The once true conversion of B is 60%, and the overall conversion of B to products for the overall process is 90%. Determine the recycle ratio, which is the moles of the recycle over the moles of the fresh feed. So this one is the reaction equation here. First, we draw the process flow diagram. So of course, we have a recycle stream and we have a reactor, and because it says a stream of pure B is separated, meaning to say after the reactor we have a separator and the separated pure B is being recycled back to the feed. So this is how we draw our process. So you have your fresh feed that goes in. Now, this fresh feed will mix with your recycled B. We call this the recycled stream. Okay, the B will mix with your fresh feed and forms your inlet stream to the reactor. The reactor reacts and it will give you A, B, C, and D. Why A and B? Because it did say that we have one true conversion of B is 60%. So B is not fully reacted. We for sure have B coming out, and we have excess A. So we should have A coming out as well. Then we have our products C and D. Okay, moving to the separator, it will separate a portion of B, but your product will also contains B. Alright, so the first step is to take a basis. We can take a basis of 100 moles of B, because it did say that we have 20% of excess A. So in this case, we take the feed in terms of the components itself. Instead of like how we normally do, we put an F here overall. So this is the reaction again. Now we should do a stoichiometric A. Let's say that A is fully reacted with B. What is the required A? We have 2 moles of A requires 5 moles of B to react. Therefore, to find the stoichiometric A, we will take the number of moles of B and multiply by its ratio, and we get the number of moles of A in the feed, which is over here. And we are given that we have 20% excess A. So this one is actually 40 moles of A. Sorry, 40 moles. So we have 40 moles of A multiplied by 120%, because we have 20% excess, we get 48 moles of A that actually goes in. And we know that we have a overall 90% conversion of B, meaning over here. The overall conversion process of B is 90%. Therefore, we can take, so the remaining 10% is your number of moles of B that comes up from the product here. The overall means, if the question says overall, it means this border. Okay, that's why it's the product here. So take your number of moles of B from your feed, multiply by 10%, which is the remaining part of the B, and you get 10 moles. Then we will need to find the extent of reaction to continue our process, since we are given the overall conversion of B. So F is equals to negative the stoichiometric ratio of B multiplied by the extent of reaction divided by the number of moles of B in the feed, which is 0.9. Substitute the values in and we get the extent of reaction to be 18 moles. So remember this equation from previous tutorial. We will use this equation to solve for the rest since we have found the extent of reaction. So the number of moles of A in P is actually what goes in, the number of moles of A in the feed, this one is N in, plus the extent of reaction multiplied by the stoichiometric value, constant, which is 48 moles. And this one, we already found it is 18. Based on the equation here, A is on the left hand side and the constant here is 2. So the stoichiometric constant is -2. You should get 12 moles. Do the same for C and D. For C, you have your number of moles of C that goes into the feed plus this. So it's for C. But we don't have anything that goes into the feed. We don't have any C that goes into the feed, right? So it is 0 mole. But it is reacted. There's reaction. That's why we use extent of reaction. So the reaction there gives you 54 moles of C coming out from the product stream. Then for part D, it is also same as C. We have nothing that goes into the feed. We have no D that goes into the feed, but it is reacted, which gives you 108 moles. Next, let's look at the material balance in the separator section. So the separator section, we have this part. Okay. So for your separator section, you only take into account of these two sides, right? Oh, no, sorry. We take into consideration of one. This one goes in. Forgot an arrow over here. This one goes out. And you also have an outlet stream, which is NB at the recycle stream. So NA out is NAP. So out is equals to in. And NB out is NBP plus NBR. Why? You see here, the separator actually separates B from, separates part of the B out, right? So this B is a sum of this B here and this B. Correct? You have more B here and it is being split. Part of it is being split, but you still have part of it here and part of it here. So you get this one we found from this part here, which is from the first part there is 10 mole plus NBR. This one we don't know yet. NC out is equal to NCP, which is 54 moles, and ND out is equal to NDP, which is 108 moles. Write everything down. We have 12 already, we know 12. We have 54. This one is 108. We have NBP is 10. NBP is 10. And we have NAP is 12. Okay. NCP is 54, NDP is 108, which is also the same for NA out. Let's write the one that comes out down. 12. B out is 10. 54. No, this one isn't 10. This one we haven't finished calculating. So this one is 54. This one is 108. Okay, the amount of A and C and D is the same over here because the separator only separates B out. Yeah. Next, we will do the material balance in the mixing stage. So this is the mixing stage, the one in circle. So whatever A goes in is equal to whatever A goes in to the reactor. The A in the fresh feed should equal to the amount of A that goes into the reactor. But because we have a recycle stream containing B here, therefore the amount of B in the fresh feed combined with the amount of B from the recycled stream equals to the number of moles of B in the stream that goes into the reactor. Okay? NB in is equal to NB at fresh feed plus NB from the recycled stream. And you have your second equation. Taking that we have a single pass of 60% conversion of B, again, we can use this equation. Substitute the stoichiometric constant of B and the extent of conversion that we have found to solve for the number of moles of B that goes into the reactor stream, which is 150 moles. Now, since we already have this, we can substitute this value into equation 2 and NBR. NB in. Okay, substitute it in here. Draw a better line. Substitute it in to solve for our NBR. So we get our NBR is equal to 50 moles. Since we already have NBR, let's solve back our equation 1. Equation 1 is over here, so this one is NBR is 50. Then we can solve for our NB, the number of moles of B that comes out, which is 60 mole. Let's write it down. Therefore, the recycle ratio is the number of moles of B in the recycle stream over the feed. Since we found NA in is 48 and NB in is 150. Oh, sorry, in the feed, not in the reactor. So over here we have 48 and over here we have 100. Right, our basis. So NBR over the total of the feet, which is 100. This one is B plus A, and you get 0.338.